So, be nice if you could see that. So here we go. So we're going to do basically not this one. Not this one. Let's go back. So this is a good start. Let's have a look here. I want to go that one. So we're going to start off with electric fields. Yes. I opened it just like a minute ago. Is it open? Is this one open? This one is open, yeah. So yeah, sorry, I thought it's one little click of one little switch and the whole thing's open. So I'm sorry about that. So let's do that. So basically we're going to start there's like 4 chapters on electricity, and then there's 4 chapters on magnetism and electricity and magnetism, and then we go on with light. So this is the beginning of our study of electricity. We'll talk about electrostatics to begin with, and then we'll talk about electric currents, and then we'll talk about magnetism. Not today, but over the coming weeks. We use IJK vectors a lot in this, so review please. We'll practice them, but review your old IJK vector materials. Yeah, let's have a look. I need a pen. Please give me a pen. Maybe this is not ready for prime time.
It's on the top right.
That guy? No, that's a highlighter. Well, I'm going to try another thing then. This is not. Let's get out of here. Cancel. Let's get out of here. And I'm going to go over to my notes, and hopefully they're the same. Electric field notes, PowerPoint, get rid of that. Let's do the enable content. Let's do the slideshow. Go here. This actually might work even a bit better. So do I have a pen here? Yes, I have a pen. Good. Okay. So then let's go from here. So basically, what we're going to do, we're going to talk about, and just confirm for me that. Oh, that's interesting. Just confirm for me. Well, let's play this. Studying static electricity.
Here we go. Charging the rod. Rod is charged. Balancing the rod. One balanced rod referring to friction. A similarly charged rod. 2 similarly charged rods together. Bring them up. What should happen? Yay! I don't know.
So let's just stop for a second. What we're doing there is we're rubbing 2 materials against each other. If the cloth likes electrons more than the plastic does, it will grab the electrons and become negatively charged, which means the rod will become positively charged. If the cloth likes electrons less than the plastic does, then the rod will grab the negative charges and the cloth will become positively charged. So you can charge by friction. Not all materials. There have to be basically insulators, and there have to be some specific kinds of insulators. Not everything will do it. What he did there was he did the same thing on 2 identical materials. So if it was positively charged on one, it's positively charged on the other. If it's negatively charged on one, it's negatively charged on the other. And people discovered these charges just by happenstance. But pretty soon, playing with them, they realized there was 2 types of charges, and they worked out the basic rules. And the first basic rule is that similar charges repel. Opposite charges attract. So it's just shown that similar charges repel.
One charged rod, I bring up an oppositely charged rod. What should happen?
Different material, opposite charge.
Opposite charges. Right. And away we go. Now this might be a little bit of probably the word, a little bit of a fudge, because not only do opposite charges attract, but neutral objects
So there is a point where you can get, if you get a neutral object, it will have a so-called polarized charge on it, and it will behave like it's an oppositely charged, so it will attract. And we can see that in a moment. Oh, you're doing that to me. Okay. So, this is going to go on a while, so let's see if it does anything else that's interesting. So now he's attracting that bottle, which is neutrally charged, with a rod. Kind of a bit eerie, isn't it? It's like force through space. Pringles. Again, it's an insulating material, so it tends to be attracted. He's going to balance his wooden look at that. Now, why is it going so much better than the smaller one was? Think back about Physics 1. Why would a big, long ruler be much more turnable than a little ruler? Well, moment of inertia is bigger on this thing, but what's that other thing that's like that? No, mass is like, no. Torque. It's much further away. He's applying the force much further away from the turning, so much bigger turning effect. So he's kind of been clever with that. And anything else? Running my mind. Enough, yeah. So that's online, so by all means have a look at that. Now, how do I get on? Okay. Okay. Same, your first slide? Is that right? Am I right? Same slide? Okay. So charges come in pairs, positive and negative. You can separate them. I could put a lot of positive charges on one side of the room, a lot of negative charges on the other side of the room. In the universe, let's say, there's the same number of positive charges as there are negative charges. They're not the same thing. Positive charge is electrons. Electron is a lepton. Negative charge is an electron. Electron is a lepton. A positive charge is a proton. Proton is made out of basically 3 quarks. In a way, they're very different things. It's amazing they have the same amount of charge on them, because they're not just like two versions of the same thing. They're actually quite different things. They discovered there were charges. They discovered they came in 2 different types. They then started saying, what are they? And what they found was they could extract the negative charges easily. And they did experiments like cathode ray experiments where they got glowing gases. Millikan. This is an interesting experiment. Millikan, it was really one of the first times, I'm not being funny now, but it was one of the first times when an American scientist really kind of set the scientific world on fire. Before then, there'd been people like Benjamin Franklin who were really quite good, but they weren't given much credit in the rest of the world because they were, you know, people who just revolted, so they were dismissed. In fact, there's some funny stories which we'll get to about Benjamin Franklin invented a lightning rod, and not to be outdone by a colonialist, Britain went and stole his idea and modified it to make it. It turned out horrible because they didn't understand what he'd done, and then said we had it first. So they made an awful version of it and said we did it first, and it was awful. But he was an American, so it was like we're not going to give him any credit. Millikan, this was the first time really that there was an experiment done by an American, and the rest of the world said, "Whoa, this is really good." What Millikan did was he basically found a way of figuring out the charge on the fundamental amount of charge you can have. The way he did it was he basically took sewing machine oil, a very light oil. He took sewing machine oil and he put sewing machine oil in a little bottle, basically. And then he used an atomizer like you'd use for perfume or something like that. And he sprayed a fine mist of oil particles into a chamber. Now, just the act of friction, actually, will charge some of these particles. But what they'll sometimes do is they'll have a little radioactive source at the side, and that will actually cause more ionization. But one way or another, you make a mist of particles. Most of the oil droplets are neutral. Some of them are positively charged because they lost an electron. Some of them are negatively charged because they got the missing electron from someone else. Chances are they don't have one electron. They might have 5 electrons or 17 electrons or 19 electrons. Getting one electron is actually an extreme, you know. So what happens is these things are so light that it's like dropping a leaf out of a tall building. They don't accelerate. They have a pretty low terminal velocity. So they steadily fall rather than accelerating. But they do fall. And they fall and fall and fall. And in the floor of this device, they have a hole. And so of this mass of charged particles, we have a few charged particles that fall through the ceiling. And so this observer looks through this microscope, and there's a light source in here somewhere, and the light shines off the oil droplet. And so, I mean, everybody who's done physics has done this experiment. It's like a rite of passage. You spend 4 to 6 hours in a dark room, staring at this microscope, looking at these little dots of light fall through the ceiling. And you have a power supply, and you can make the top negative, and you can make the bottom positive, or you can reverse the battery in effect and make the top positive and the bottom negative. And what you'll find is, say with this configuration, a positively charged particle will start moving upwards. And you can time it. And then you can allow it to fall. And you can cause it to move upwards again and time it. And you can make measurements of how quickly it travels upwards and downwards, etc. And to cut a long story short, its behavior is determined by its mass and its charge. Now, its mass affects its downward journey and its upwards journey. The charge only affects its upwards journey. So you can differentiate between the two. And so what happens is you get to a situation where you get, if this is the charge, Q, and this is the number of trials, you get kind of like, you know, one will be like that, and the next one will be like that, and the next one will be like that, and the next one will be like that. You never get 0 or 1, you get a whole bunch. And the trick with this experiment is not to do one droplet really well. The trick with this experiment is to do 100 droplets. Because what you're looking for is the smallest difference. Because what you find is that when you look at the differences, the smallest difference is 1.6 times 10 to the minus 19 coulombs. And you will get multiples of that difference. You'll get, you know, because one's got 2 charges different, or one's got 5 charges different. The chances that you will get one oil droplet with 1 electron on it is very slim. So you look for the differences, and the more trials you have, the more likely you will find a difference of 1 charge. So people do this experiment over and over again, and they find that they get 1.6 times 10 to the minus 19 coulombs, a frighteningly small number. A coulomb is actually very big. Okay? A lightning bolt might have 3 coulombs of charge flowing through it. So a coulomb is a huge unit, but this is 10 to the minus 19 of it. You know, it's like a tiny little bit. So if you become a physics major, you'll be doing this. This is a very standard piece of apparatus. Millikan's original was about the size of this desk, and this is about the size of, you know, a book. It works very nicely. If you do engineering and you want to do a minor in physics, part of the minor can be the intermediate and the advanced lab, and you'll do this experiment. So it's a famous experiment. It's very, very nice. Just a bit long for what we do. Here's a video of that.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19 coulombs. He took this to be the charge on a single electron.
Cool. So we know that there's a charge, and we know that the smallest charge is 1.6 times 10 to the minus 19 coulomb. It's still a bit of a mystery to me anyway, that an electron has 1.6 times 10 to the minus 19 coulombs of negative charge, and a proton has 1.6 times 10 to the minus 19 coulombs of positive charge, when they're completely different animals. They are completely different things. But from an electrostatic point of view, they're just opposites of each other. So, okay, how can we make charge? Well, that first demonstration showed us we basically take a rod, usually ebony or sometimes ebonite or sometimes some kind of polymeric material, and we rub it with something like, well, dare I say it, rabbit's fur or wool or silk or something like that. And what we find is that depending upon the combination, we can either leave behind positive charges, or we can have an excess of positive charges or negative charges on the rod, and that's charged. And then the question is, what do we do with it? One of the things we can do is we can basically take an insulator, so something like a balloon or something like a polystyrene sphere. They used to use pith balls, which is basically, as best as I can tell, it's orange seeds kind of mashed up and then formed into like a very lightweight insulating ball. But basically this is an insulating material, and you have a rod which has charges haphazardly positioned on it. An insulator is an insulator because it does not let charges flow around it. Insulators hold on to charge and keep them in a given place. So if you're using a butter knife to butter bread, the butter kind of goes where you put it. And so, same thing with this. I get a bit of a haphazard pattern of where I put my charges onto the insulator. And so when I take this rod away, there's fewer charges on it, and I've left some charges on here, but I have no real idea exactly where they are because I can't see charges. So you find this insulator behaves a bit haphazardly. If you're near one side, there's not much charge evident. If you're near the other side, there's a lot of charge evident. Seems like a disaster. But then imagine this. You take an insulator and you somehow manage to put a pattern of charges on it. You then sprinkle some powder over. The powder, like static cling, like your socks to your shirt, gets attracted to where there are charges. You then put it through a heat press and you have photocopying. It's the same principle. So, in a way, it's good that the charges are allowed to run around on an insulator. In some circumstances, it's marvelous. In other circumstances, it's a bit frustrating. So we tend to do experiments with not insulators, but with isolated conductors. So what we do is we take a metal sphere. So where's my pen gone? We take a metal sphere and we take a metal sphere and we rub our charges onto that. When we take our charge rod away, yeah, there's some charges on this, but the charges on the metal sphere spread out. They get as far away from each other as they can, and so there's a much more even distribution. So the trick with this metal sphere is it is insulated from ground. We don't allow it to touch the earth, because the earth is so big that any charge which is near any other charge sees the earth as an escape. So the charges will always try to run to ground. And so sometimes we will ground things to protect ourselves. So in your house you have a grounded cable, which is literally to a water pipe, or literally to a pipe that goes into the backyard, to the earth. Or other times you will, electric workshops will have wooden pallets all over the place, because they don't want a connection to ground through the person. So they'll ground the desk, but they won't ground the person. Actually, there's a funny story. When people make semiconductors, a little bit of charge on an operator's hands can damage a chip. And so they had this problem when they first began, because automation wasn't the way it is. And so people had to physically handle some of these things. And so the final packaging was a huge big deal. And so in order to stop electrostatics from killing the chip you just spent thousands of dollars making, they would put a wristband around the worker, and there was a chain on the wristband that went to the desk, which went to ground. And I remember reading a book about revolution in semiconductors are going to change the world. It's very interesting. It said, this was in 1972, it said, computers will change everything. People will be thrown out of work because of computers. Because computers will do the job that people do now. And there'll be mass unemployment. And I naively was thinking, we could all send our own computer to work. Like, you know, I'll just get a job but send my computer. Not thinking that, no, the factory owners will have the computers and, you know, they don't need my computer, you know. But then the other thing I knew that was complete misunderstanding was it talked about how, and in some semiconductor factories, they chain workers to the bench. And it was like, well, it's not quite like that. They're chaining them because of electrostatics, not chaining them because they want to get a full 8 hours of work out of them. So it's kind of interesting to see, you know, how I'm naive on one side, and the social scientists are kind of naive on another side. Anyway, okay, so we can charge things up, and when we charge things up, there's a force between them, and this is an electrostatic force. It is very analogous to the gravitational force. Why? It's very analogous because in some ways they behave the same way. One object is affecting another object. So in gravity, we had one mass, and the other mass, let's call it little m, and let's call it big M. And there was a force of gravity between, and that depended in part upon the separation. And so you could say, well, the force felt by one of these guys was dependent on the little guy's mass and dependent upon the big guy's mass, and it got weaker as the two masses got further away from each other. And because it's spherically symmetrical, the sphere of influence of this guy is spreading out in all directions spherically. So that makes sense. It's an inverse square law, so this will be over r squared. If I double the separation, I get 1/4 the effect. And then, well, I need some constant to make this equal sign go in, so I'm going to put big G there. And that's what Newton did. That's exactly what Newton did. Well, now we have one charge and another charge, and we have a separation, and the effects of this guy spreads out in all directions, so it's going to be an inverse square relationship. And so we have one charge, the other charge, the separation squared. And to make the equal sign work, we have a constant proportionality, which in this case we're going to call Coulomb's constant. So it's the same equation with just different parameters. So it's kind of amazing if you're comfortable with Newton's law. This is the same physics. We say the electrostatic force depends upon the magnitude of each charge and the separation between the charges, and here's our basic equation. And my Coulomb's constant is 9 times 10 to the 9 Newton meter squared per Coulomb squared. Bit unusual units, but you get used to it. And I generally don't care about you calculating a value using the true value of KE. I don't mind you leaving KE in your test answer. It's just a constant. Sometimes for homework I'll ask you to work out the true numerical value, because it's good to, every now and then, to get a feel for the size of things. But for tests I don't care. Q is measured in coulombs, and then R is measured in meters because it's the SI system. Now, funny story. So this is a very typical physics class equation. And in electrical engineering, they will teach you that KE is equal to, so they'll teach you that this is equal to, they'll teach you that this is equal to QQ over 4 pi epsilon naught R squared. And it's just a different nomenclature. It turns out that KE is equal to 1 over 4 pi epsilon naught. And so the physics people tend to talk in terms of KE, and the engineering people tend to talk in terms of 4 pi epsilon naught. And the first time you see the other conversation, it's totally off-putting. So sometimes you'll pick up an old textbook and you go, what's this equation? Because it's got the old terminology or the EE terminology. So just watch out for that. Don't be tied to the symbols, you know. Epsilon naught is a fundamental universal constant. It's called the permittivity of free space. And there's another fundamental constant called the permeability of free space. Permittivity is for electrostatics and permeability is for magnetism. Two fundamental constants. So in some terms, I have to say that the electrical engineering departments go back to a fundamental constant, whereas as physicists, we tend to deal with something that's a little bit more kind of convoluted, you know. We're not going quite back to basics as much as they are. I'd like to work in vectors. And so basically I have a vector force. And the vector force, I have to be clear about which force I'm talking about. So I put down FB on A. The force exerted by B on A. So this is what A feels. So this is FB on A. That's what I mean by it. And that's because in this case it's attraction. It points in that direction. And that equals, well, KEQQ over R squared. That's my old equation. All I'm doing is I'm adding a unit vector to make it into a vector. Unit vectors have a magnitude of 1. So the unit vector doesn't change the size, the numerical value, but it adds directionality. So our unit vector has to point in the same direction that my force points. Now the book gives you a kind of shorthand way of figuring the signs out. And it's cryptic. It's so clipped. My experience is half the class would get the sign right and half the class would get the sign wrong. So my desire is that you all get the sign right by getting it from the diagram, not learning it's minus on a Tuesday if you do it this way around, you know. So what you do is you look at your diagram and you say, which of these two forces do I want? And then you look at the information you have for the separation. Did I give you that vector for the separation, or did I give you that vector for the separation? and you say, how does the force direction compare with the displacement vector? If they're in the same direction, there's no need for a negative sign. If they're in the opposite directions, then somehow I have to turn this vector around. And I do that by making everything that's positive negative and making everything that's negative positive. So my honest opinion for you is that you work out the signs of everything from the diagram. And I think it just goes much better than if you just learn it's a minus unless this is happening, then that's happening, and it's not so good. So let's do one. I'm sorry, I'm losing my pen. There. So what is the magnitude of the force experienced by a 3 Coulomb point charge that is located 4 meters from a positive 12 Coulomb charge? So let's have a look. Let's draw a diagram. So I have a 3 Coulomb. I'm going to call that 3 Coulomb positive, 3 positive. And then I have a 12 Coulomb. That's 12 Coulomb. And that's going to be a positive. And this separation here is 4 meters. So if you like, this can be little q, this can be big Q. I want to know the magnitude of the force experienced by a positive. Well, this is going to be attractive or repulsive force. Repulsive because they're both the same charge. So there's my F. And I don't really care about the direction in this case because it asks for the magnitude. So the actual sign of this doesn't matter. But I recall that F is equal to KE. It said Q1, it said QA, QB. I actually prefer little q and big Q over R squared. So there's my basic expression. I'm going to leave my KE in it. And then my Q, what's my little q? 3 positive, doesn't really matter about the positive because I don't care about the direction. What's my big Q? 12. What's my separation? 4. And of course it's 4 squared. So F is equal to 3 12s are 36. 36 over 16 KE, which equals, what's that going to be? That's going to be 18 over 8? 9 over 4, thank you. 9 over 4 KE, which equals 2.25 KE. And what are the units? I'm trying to find what? So I'm trying to find a force, so it's in newtons. If I work in standard units, I can just put down my standard units. So not so bad. It's basically just remembering the equation and shoving numbers in, yeah? What is the magnitude of the force experienced by the 12 Coulomb charge? So what's this going to be? Just tell me it. Same. Remember Newton's, which law was it? First, second, or third law says the action force is equal to the reaction force. Yeah, Newton's third law. So if this is 2.25 KE newtons in that direction, I don't have a different coloured pen, but basically this force is the same, 2.25 KE newtons. It's just going to be in the opposite direction. Okay? So not bad. This is just like gravity. Yeah? Let's go down here. Positive 3 Coulomb point charge is located at, oh my word, everything was going so nice. That's 3 positive. This here is 2I plus 3J plus 4K meters from the origin. And this guy, which is 12 coulombs, positive. And this is at 3I plus 5J plus 1K meters. Now that's a bit of an issue, because what I got to do is, what is the vector force experienced by the 3 coulomb charge? I know it's going to be that. There's my force. But I need to find the vector which goes between these two charges. I need to find that vector. I need to find that vector. I have that vector, and I have that vector. Let's call this R1. Let's call this one R2, and let's call this one R3. Thinking back about your vector addition, which two of these add together to make the third? We have R1, R2, and R3. Which two of them add together to make the first, to make the third one? There's R2, there's R3, there's R1. So can you write down the expression for me? You know, R2 equals R1 plus R3, or R3 equals R2 minus R1, or something. Which two of them add together to make the third? Well, let's not do minuses because it's going to drive me crazy. But you're right. It's going to be, this is the guy, this guy over here. That's the guy which is the resultant. And those guys are added together. So I say R1 is equal to R2 plus R3. Not because I named them like that, but if you look, that guy is added to that guy. The process of addition is putting the tail of the second one on top of the first one. I'm sorry? Negative? Negative R1. No. R2 plus R3 equals R1. There's my R2. There's my R3. Those two added together equal R1. Now, I want to find R3. Yeah? So I can say, well, R3 is equal to R1 minus R2. Okay? Agreed? Agreed? Let's do it. IJK. So R1 is 2, 3, 4. And minus R2, minus 3, minus 5, minus 1. This is R1. This is minus R2. Add these two guys together. Minus 1, minus 2, plus 3. Agreed? So that vector there is minus 1I minus 2J plus 3K meters. And that's not really electrostatics. That's vectors. Okay? That's just like a preamble, but I'd like you to be able to do that. So now let's do the electrostatics. We say F is equal to KE Q over R squared times R hat. So F is equal to KE. What's the Q? The little q is 3. The big Q is 12. I don't actually care about their signs. I'm going to take care of their signs by the direction of my vector. Over. How can I go from a vector and find its magnitude? What do I do to find the magnitude of an ijk vector? Oh yeah, so I do. And that's going to be minus 1 squared plus minus 2 squared plus 3 squared. Agreed? Yep. Now, is that r or is that r squared?
That's R.
So I need to square that. Okay. There's my magnitude. All I need to do now is work out this unit vector. This vector, this R3, points in from 12 to the 3. Is that the same direction or the opposite direction to the F? It's the same, isn't it? It's pointing in that direction, and this guy is pointing in that direction. So I don't need to do anything about that. I don't need to turn it around. I just need to make it so this unit vector only has a magnitude of 1. This R3 is in the right direction. So minus 1i minus 2j plus 3k is in the right direction, but it's too big. It's not a unit vector. How can I make this into a unit vector?
By the magnitude.
So I divide it by minus 1 squared plus minus 2 squared plus 3 squared. Almost there. What's missing? Don't get lost in the detail. You have an answer. Yeah, good. I need newtons. Don't forget your units. If I, in a test, say, write me an expression for, that's exactly what I want. I can look at this. This is like looking at somebody's bones. I can look at these and say, do they know what they're doing? If it drives you crazy, I don't mind if you go, F is equal to 36 KE over, and that's going to be 1 plus 4 is 5 plus 9 is 14. 14 times minus 1i minus 2j plus 3k over the square root of 14 newtons. I can live with that. But if you mess up in going from here to here, I might not spot that it's right back here. I might just look at this answer here and say, this is not right. So, you know, don't go crazy on it. If I say, write me an expression for, that's code for what I want. Okay. We did this, I think, with good old Newton's laws. It's the same skill. Okay. Let's draw a line there and let's come back next time. Okay.